Welcome to lab number 2. This lab is similar to lab number 1 in that we're still working with electric fields and equal potential lines. So let's just recap some of those ideas. So in the first few chapters of this lab and in the lecture courses 201, 202, and 102, we're dealing with three big ideas. Those are electric forces. Right, that is the F equals KQQ over R squared. The electric fields. Electric fields are a force per unit charge, and electric fields are given by this equation, KQ over R squared. At least the magnitude of the electric field is given by that. Of course, it's a vector quantity. And then finally, potential. Later, we'll use voltage to refer to this. We'll have a whole chapter on potential. And potential is an energy per charge. And the way that we calculate potential is V equals KQ over R. So those are the three big ideas that we're dealing with in these electricity chapters: forces, fields, and potential. Now, in the previous chapter, you dealt with this configuration of charges, a dipole, where you have one positive and one negative charge. I can draw my electric field lines, and I do so by taking an imaginary positive test charge and placing it right here, and the direction of the force gives me the direction of the field. Now I'm going to have one force that's pretty big and up in that direction, and then have another force that's like that, and so the electric field will look like that, the combination of those two. If I draw the electric field lines, as you did in the previous lab, they're going to look sort of like this. They go from positive to negative charges, and these are the lines of force. They describe the force that a positive particle would feel if it were in that electric field. So for example, if I had a positive particle here, it would feel a force in that direction. And that force comes about from Coulomb's law. We can calculate it. It has two components, the one due to the positive charge and the one due to the negative charge. So that is our electric field. In that lab, we also talked about equal potential lines. And equal potential lines are lines that are perpendicular to the field lines. This is an equal potential line. So for example, let's say that this equal potential line has a potential of 10 volts. This one, as I get closer to the negative charge, would have a lesser potential. As I get over here, I find that this has an equal potential of minus 10 volts. So my equal potential line will change as I move around within the electric field, but the equal potential line will always be perpendicular to the field lines. Also, as I have a charge that moves along, say I have a positive charge, if it moves along this equal potential line, there is no work or no change in energy. And this gets back to our original idea that potential is energy per charge. And so if the potential is unchanging, that means that the energy is unchanging. In order to have a current is a movement of charge, not like a political movement, but you know, actual movement. We'll talk more about charge in chapter 3 in the lecture course, but or about current in chapter 3. Current is a movement of charge. In order to have a current, you must have a potential difference. That means that charges can move from here to here, from a high potential to a low potential, because there is a difference in potential. Look, we've seen this idea before when we talked about the Earth. This is a picture of the Earth. There is a gravitational field around the Earth, and the gravitational field looks like this. Whoops. Looks like this. There are also equal potential lines. Oh, shoot, I'm sorry, y'all. They look like that. So I can have a mass move within the equal potential, or move within that field, and it will experience a change in energy if a mass moves from one equal potential line to another equal potential line. We didn't talk about gravitational fields in that way just because it wasn't necessary. But now that we're dealing with electric fields, it will become necessary to think about not only the fields, but also the potential. All right, so a potential difference is needed for a current to flow. And a test charge in an electric field can move anywhere along the equipotential line without doing any work. There is another topic in this, really an instrument that we will see when we do the procedure part, and that's called a galvanometer. You don't really need to know about this much right now, except that this is a device to measure current. We're going to talk more about a galvanometer. In your lab manual, it describes how this consists of a coil of wire through which a current flows. So I have a current flowing through this coil of wire. A current, remember, is a movement of charge. So I have charges moving through this coil of wire. And then there's a magnetic field that this coil of wire sits within. The end result is that when a current moves through this coil of wire, it experiences a torque. Remember, torque, which will cause that coil of wire to move. Based on how much the coil of wire moves tells us what is the current. We'll have a whole lab on galvanometers, and we'll learn how they're used in other devices which are called voltmeters or ammeters. When you have two equipotential lines, or when you have 2 points in space, say you have a point here and a point here, and you have our galvanometer, which I'm just going to label as a box right here, and you connect 2 leads to these 2 points. If the difference in the potential is equal to 0, that means that there is no current. If the difference in potential is not equal to 0, more than or less than 0, that means that there is a current. So we'll be using a galvanometer to identify points of equipotential. I'll show you that in the procedure on the devices, but that'll be a very important idea that if I have no difference in potential, that is, if those 2 points have, the same energy per charge, then there is no current. Again, back to our Earth analogy, here's our Earth. If we have an object that moves along an equipotential line, and an equipotential line runs like this, say on the ground level, if this object moves along that equipotential line, there's no work. In fact, if I have an object sitting right here, unless I exert a force on it, it's not going to move at all. And so you can think of it in that way, that if I have an object that's on an equipotential line and moves along that equipotential line, that there is no current. That really, I have to have an object that moves between 2 different potentials. So if I have an object here, it will move to a lower potential state. All right, that's all. I will show you the procedure in another video.